So again, thanks for being here. So the title of my talk is Sequence-to-Sequence Model on Time Series Data. So I'll work on the model development and exporting it, as well as on serving it with TensorFlow Serving. So I'll try to go over all the steps so that you can basically reproduce this. I'll have a slide at the end of this, which you can, if you want, take a picture, but I'll probably share this as well, which gives the code is already on GitHub, so you can basically take the code and reproduce everything that I'm showing here tonight. And so this is basically more slides to guide the discussion, and then I'm going to jump into the Jupyter notebooks that have the actual code. So just quickly on my technical profile for the ones who do not know me. And then second part, model training, optimization, export. This is a bit of a longer Jupyter notebook that I'll walk you through. The second Jupyter notebook is a model serving and sample client code. This is smaller, so again, I'll jump to that and I'll show you how that goes. And finishing with some final notes and Q&A, as I said. So just about myself, I worked about 10 years on in telecom networks, in computer networks, for protocol development, modeling, mathematics, and software development, and that is all before the first element on this list. So I did a Ph.D. afterwards on a computer network security problem. So it was a model development with continuous time Markov chains, and then analyzing what it was predicting with the actual data that was being collected in the industry by a corporation called Dumbbell Corporation. And then I went in the industry, worked on a variety of data science projects, big data applications, optimizing on the Hadoop platform for different companies in different industries. I did several deep learning applications, major ones, one for Intact on the UBI program, which was about transport mode detection on the phone. So it was a TensorFlow project. And after that, one for CN, which was image recognition, object within object detection. They were interested in detecting cracks in equipment. And so I developed a double layer convolutional based network for them. More recently, a data mining application for a company in telecom, which was about detecting patterns in the stream of alarms that are coming from telecom network equipment. So they get flooded with too many alarms. They were interested in detecting the patterns, both for detecting the systematic problems, but also reducing the redundant alarms. And throughout this whole journey, basically, I ended up, as you probably have noticed, I had data science related titles, but I ended up working a lot on platforms, because the platforms that I was working on did not have the components and they were not properly configured. So I ended up working a lot of platform work at the beginning of each project, and that led to basically what we developed recently on UniAnalytica, which is a platform in-house we built from scratch from different open source projects, which is basically pre-configured and has the components that basically I've been using in the past few years. And you can know more about it on unianalytica.com. So the product is fully transparent and I explained. I'll be using the same platform actually right now in the live demo. We are using basically two nodes. So there's a CPU worker and a GPU worker. The GPU worker is for training the model and then saving the model, and the TensorFlow Serving also runs on the same worker. And there's a CPU worker, basically the client who sends a request, prediction request, and gets the results back. So we're going to use basically two distinct nodes. So there's no clustering work here. It's not Spark or let's say distributed training with Horovod, etc. Two nodes, one CPU, one GPU that we're going to use for the demo today. So this is the first Jupyter notebook that I'm going to execute as we go along, and finger crossed, nothing breaks. And so this is the model I'm going to actually explain right in the middle. Just a brief overview what's a sequence-to-sequence model is, in case you're not familiar. So the explanation will come. The model is based on a work by Guillaume Chevalier, who I found his work sometime earlier, and some of the code snippets is from his work, which is linked here. And then there's a feedback mechanism to add to the decoder input of the sequence-to-sequence, adding a feedback mechanism. That part I got an idea from Wayman Wang, and so kind of a combined solution here. So as usual, some package imports here, nothing much going on here. The part that I'm going to probably explain right here is that, so the code right now, as you see, it's running right now with the last stable version of stable version of TensorFlow, 113.1. But if you want to run it in well, when the 2 version, the stable version comes out, if you want to run it, probably you need to change this code if you really want to run everything in TensorFlow 2. So this is kind of like TensorFlow 1x code. And there is also some, actually, it was basically the earlier implementation of sequence-to-sequence model. So we are using some of in more recent TensorFlow versions, the API has changed a bit, so we are mapping some of the functions here on top, as you see. And that's about it. So the code runs on latest TensorFlow. That's probably the takeaway here. But if you want to evolve and run it on different versions of TensorFlow, whether earlier or later, you probably need to change the code. So we have the requirements file for the Conda environments on GitHub as well. So if you want, you can just reproduce, know exactly what this environment is. So this is, I'm going to take some time actually explain what the flow of this training is. So this notebook, I use it a lot. Similar workloads I use for different models. So starting here, so maybe global view is that we have a parameters dictionary, which basically holds all the values, global values, paths on the disk and everything. So including, some global parameters regarding the model that will not change throughout the experiment. If you want to do a grid search, you're not doing grid search on these parameters. These are fixed from one experiment to the other. So we've basically, a params dictionary is basically holding that. We have several paths, experiment results saved, sessions of TensorFlow are saved here, and then models are exported here. Some plotting, random plots that I'm going to draw to make sure that everything is fine. We have a sequence of 10, imagine 10 days of time series, a time series of basically 10 days, and then we have a prediction of the following 5 days. So that is what sequence in and out mean. Input dimension, we have 1 and 1 here. And that's what I'm going to show. But the code is ready to go multidimensional, which means that here I'm going to show basically one time series coming out and prediction for another time series. But you could have any combination. Let's say multiple time series coming out, predicting one, and that is when you want to have different variables. Let's say weather and stock data and traffic. You can all put as input and then have the stock price as output. So you can play with this in different ways. The code is, the mock data that we are generating is a sine wave, just a simple sine wave, and the model is going to learn that. So it's very simple function, and so really the training is going to go fast. And for that, we're just setting as to 1 and 1. Data set size, basically 1,000 pairs of these time series that I just showed you, I just explained to you. And we divide it by basically 60%, 20-20 between training set, validation set, and test set. And the rest is basically some parameters which you probably are familiar with on from any machine learning optimizer. And here is the parameters that we want to grid search on. So we basically took here 3 parameters. This is the hidden number of hidden dimension, which is basically number of cells that are in each layer, and you'll see in the picture what that means. So you can bear with me. Layers stacked is the number of layers. So in encoder and decoder, how many layers of cells we want to have. And then the third one, sequence to sequence type, is basically the whether or not we want to. So here I've put 2 options: whether use the original sequence to sequence which was in TensorFlow, or use that decoder feedback that we added. So basically, so not only I'm playing with parameters, but I'm also changing network structure in the middle. I just want to see how they compare together. Which one gives me the best result. And that's the good thing about this. And really going by hand and coding it is that you can just play around and mix and match. So sometimes people do grid search on it with a GUI that just lets you add one value for something and choose your parameter and add value. Here I'm basically doing grid search on portions of code, which could be anything. It could be part of your data engineering part or actual network part. So here basically 2 values per parameter. So we end up basically with 8 combinations. So basically we have here 8 experiments that you're going to see. Just some directory creation here to save the results on disk. That is the Dataset Generation, and I can explain that later if needed, but basically it's a sine wave that we generate random sine waves, thousands of them, and we use them for our data set. And I can come back and explain this if you have time at the end, but there's not much to it, frankly. It's a very simple part of the code. That is actually what you want to switch out if you want to, and for sure you want to run it on your own data set and your own problem. That's the part that you're going to take out and you basically put your own data in. So just quickly on what the sequence is, as you see, there's an embedder here, and there's a embedding here, and there's an encoder, and there's a decoder. So, sequence to sequence is almost all exclusive for language problems, and that's why this graph is for language. So it's how are you, and then there's I'm good. So sometimes it could be in English, this could be in French. So that is how the idea of translation models work. It's a very simple one. There are more recent models on language translation are much more sophisticated, but this is a basic structure. And this is the feedback mechanism that I mentioned. So we feed one of the output of a cell here to input of the cell nearby, and this is the feedback mechanism. So in the original implementation, this was not there, and this is the addition that I mentioned at the beginning, which you can add or not depending on that parameter. And that is what I just said. So in order to add that decoder part, that feedback part, there are some overrides of some functions, like 3 functions, and I'll let you read that later on, which basically add that feedback mechanism to the model. That's basically it. So this is a large function that I'm actually going to take some time to walk through it with you and explain. Basically, most of the stuff happens here. As a run experiment, it picks up the experiment that we have, which is one of those 8. So one of those 8 experiments that we had. So it's like 3 parameters, each of them having 2 values. So 8 combinations, 8 experiments, and this is a dictionary that has the details of one of the experiments. And this is the dictionary that has everything else, all the parameters, paths, and everything else that is needed. And this is the data set. So we're going to call this function and I'm gonna come back to it and explain to you its details. But let's just call it and see how it works. So this is running right now, and so it's like 4 of 8, and it's going to go to 8, and I'm going to just come back up and explain what it shows. And this, you know, we are running on a GPU machine, as I said, but because the data set is small and the function we are learning is small, this actually goes pretty fast, and it learns pretty well too. So for this one, you can actually run it on a CPU in maybe 2 minutes, if it's not too bad of a CPU machine. So what it does is that, you know, experiment 1 of 8, there are details of that experiment, which is basically the 3 values for those 3 parameters. So hidden dimension here is 12, we have 1 layer, the sequence type is the original one. And it starts the training, and then it shows the loss of training and validation, so you can monitor how it's going, whether it's going fine. And that is a picture that you know, just to give you visualization of what this actually meant, the whole thing. So this is a sine wave, this is the input, and then the predictions are yellowish, and the actual values are blue. So you see that actually sometimes in some experiments near perfection it really learns it well, but bear in mind that this is a very simple function. You know, it's really bare minimum. So you got to do some work and fit it, you know, fitting it to your data to make sure that it works. It doesn't work out of the box all the time. You gotta work on the model optimization. So after it's done, each model is saved here, which is basically saving this session of TensorFlow so that we can actually read it back up and on the test set at the bottom of the code when we want to basically have the results on the test set. So right now we are checking the training and validation set, but we want to ultimately at the end see how it's behaving on the test set. So that's why we are saving the session 2 so that we can read it back up at the end. The model is also exported, and that is for the purpose of the TensorFlow serving, so that we can serve it with TensorFlow. I think we're good here, and I'll get you some perspective on what is the last part is. So that is the part that I just explained. So this is the best experiment. So this is basically picking up the 8 experiments, sorting it by validation loss, and it picks up the first one with the lowest validation. So it says that, for example, experiment with ID 6 has the lowest validation loss. So this is all sorted of the 8 experiments we had. So we know that, you know, this experiment has the best result. And then this part now we switch to seeing how the model performs on the test set now. So again, the same process if we want to choose. Here just a code snippet so that either you test the model on the best experiment, or you just say, no, I want to pick up this experiment and say how it behaves. So you can basically give a value to this chosen experiment ID, and it's going to run that model through the test set. So this is kind of like if you want to override what model should be used during testing. So during testing is basically creating the graph, recreating the graph. So it's a bit of boilerplate code here. You need to give again names to the input and output tensors. So when you read back up the graph, you need to the tensors that you're gonna call during training here. Let's say for having the fit dictionary, we are calling this tensor, we are calling this tensor, and then we are running the session on these two tensors. So these four, they need to be identified here, otherwise it's not going to find out. So when you're writing your graph, it needs to have those names in the graph so that you can come here and call them back.
Would you please zoom?
Thank you. I forgot. So we are plotting also, as I showed you, nothing special here. Almost perfect on the even test set. This one is actually not that perfect. There are some that is not good, but it usually is good. I mean, this is already good for a lot of applications that you might want to have. So I'm going to just come back up and maybe spend 5 minutes on that large function run experiment that I told you about. Maybe spend a few minutes on this, just so that you get a sense of how this is working. So at the beginning, we are just combining these two dictionaries together. We're basically putting experiment in parameters. Nothing special, just so that we can get to the experiment, because right now within this experiment there's one experiment, so there's one set of values. So we just combine them here and then just turn everything to just local variables so that the rest of the code is linear. So basically, hidden dimension, for example, is going to be just hidden dimension from now on, and the rest is similar. There is a dictionary that holds the results, experiment ID, training loss, validation loss, parameters number. This is just so that we know, have quantification of how heavy the model is. It basically counts all the weights and everything else that is in the model, just so that we have a sense of how heavy this model is. So we count that, we save it in the parameters so that we know. There's a duration so that we know how long training this took, so that we can. If you want, we can put a stopper on that. Sometimes if you train on something, it might get to a situation that it takes forever. So you might want to check time sometimes and just abort the experiment if it's taking too much time. This is the code of that graph that I showed you earlier. So there's input tensor for the encoder. There's expected output. Here we are creating the layers, and there's one single snippet which is for both layers, for encoder and decoder, but the weights underneath are not shared. That's just a TensorFlow implementation, so don't be alarmed that we are just creating one. It's going to be used both in the encoder and decoder, but the weights underneath are different. And this is the part that I was talking just earlier, that depending on type, you can either, so this is the original one, and we are calling basically the native TensorFlow function. And if we want to have different versions, the functions that I just skipped over at the beginning that are like overrides, if we want that, then we are going to just call that override function. So it's basically just a modification to add that feedback loop to the decoder part, if you want. So this is one of the parameters that we are using during the grid search. Depending on what the value of this parameter is, it's going to pick up one or the other of architectures. This is one of the grid search parameters here. We're calculating L2 loss, adding regularization and optimizer on the loss. This is just a code snippet, and you can thank this person for it. Just counting the number of parameters that are in the model. Running the session now, and this is basically picking up the graph, going through it, running the training optimizer and the loss, so it cycles through that. Every 10 batch, we also look at how the results are looking on the validation set. So we just save that so that we have those graphs of training loss and validation loss, so that we can see how the training is going. Is plotting loss? We were seeing the graphs earlier, so that's where the parameter is set that yes, plot the loss please. The same about plotting predictions. This is basically if you want to switch off and switch on the graphs. So if you are running, here we have 8. Sometimes with Spark we run like thousands of experiments. We don't want to generate graphs for everything, and nobody's going to look at that. So we just turn these off, and so basically the whole thing is linear. Duration, just a call to the time, basically seeing how much this experiment took, and saving the session on disk. And this is from here up to end, basically exporting the model. Nothing much here except that if you want to change it, you gotta now go back to look at, learn a bit how TensorFlow Serving API works. And there are different signatures for input and output. So if you want to change it, you will need to know about that. But if you don't want to change it and this works fine, you're good. You can just leave it as it is. So these are basically input and output defining. And we are using the prediction, the predict signature in TensorFlow Serving, which is basically the most general API that it has. So there are some higher layer APIs, signatures, like I think regression or classifier, which are more strict. And then prediction is, you can do whatever. Basically, it's a tensor in, tensor out. So you can basically, yourself, you can define, is this a regression problem or is a classification problem? So we're good with this. I'll probably take questions at the end because I think I'm short of time. So just a few notes here on the grid search. So there is I just throw out a little thing that, if you run thousands, how do you want to interpret that? The grid search is multidimensional space. It's better to visually see where the optimal solution is rather than just sorting it by one parameter and selecting the best one. Sometimes there's a kind of like outlier that gives the best result, but it's not the best region of your optimization. So it's one thing that I may present later on. The other one is if you want to do, you want to optimize simultaneously on multiple parameters, doing a grid search is going to explode. Basically, the number of combinations is too high, and for that there are different methods. There are random search, Bayesian optimization, and what we would recommend is hyperband. Is one of the is the state of the art, is outperforming Bayesian optimization. There's a paper for that, and you can find about it. So this page that I'm showing is basically our machine learning stack in UniAnalytica, and the part that you probably want to take a look is the number 3, which is what I just said. So you can actually have this, see this if you wish later on your browser. So you go unianalytica.com, you will see, and the link of hyperband is there. Actually, you can just Google hyperband. It should be coming up as the first results. So hyperband basically is a smarter doing of grid search. It's finding the result much faster, and it's very efficient if you want to do multidimensional on different parameters at the same time. It gets the result faster, outperforms existing methods. And the people behind it actually, so on that link, if you click on their page, you would see that they have made comparison on different data sets, different classical ML problems, and they are showing that it's really outperforming. The number 2 is Spark, is basically if you want to so here we are just running it one experiment in one thread of Python basically, but if you want to spread it over a cluster, go faster, do things in parallel, we support that too. Now, showing the model serving and sample client code quickly on that, and I'll take the question at the end. Apologize for it. So this is the second Jupyter notebook that I was just talking to you about at the beginning. So the parts that are important here, I would say, we are picking up basically the visualization code from Guillaume's work, but the rest of it is basically some codes from the TensorFlow Serving API and guides and snippets that we've taken from there to help us write the client side, basically. It's not using TensorFlow, so that's an environment, basically it's using some basic packages, but there's no dependency on the TensorFlow from the client side when it sends the request. So this one, it's basically running the TensorFlow Serving on the GPU machine. So it basically, we set the GPU runtime. The Docker image that we have is a custom one that we've compiled on our own platform so that it matches perfectly with the CPU version, GPU version, CUDA version, cuDNN version. But if you want to use the off-the-shelf TensorFlow binaries for TensorFlow Serving, you need to change this so that it goes and fetches that from Docker Hub for you. So probably this part you will need to change. The rest of it is just giving a path, and I'm just picking the experiment 1 model that was just generated when I ran on the training side. Just giving a name to the model here, and that's about it. So I need to basically shut the kernel on the training side so that the GPU memory is released, because I'm running the TensorFlow Serving parts on the same machine. So it goes, basically says that I'm ready, and this is the success message. Basically, it's now listening. So TensorFlow is listening, and I can now run this code. This is running, the client code is running on the CPU worker. So these are 2 different machines. So just few imports here, and that is the IP address of the TensorFlow server, so the GPU machine, the port that is running, the name that I just gave when I launched the Docker thing, the model version. When we trained the model and exported, we said that here's our version, and then TensorFlow Serving actually can serve multiple models, each its own version, so it can do simultaneous. So we can decide on the client which model we are calling actually. This is dataset generation, just so that we need to generate the first part. Let's say the 10 days and the 5 days. We're generating the 10 days here so that we can send something. So this is creation of the URL, basically giving the host address, port, model name, version number. So basically creating that URL that we are calling. We're then sending it to this function that opens that URL, sends our data, and gets a response back. So it's actually pretty low overhead, like few lines of code to actually write a client in Python. So just printing what it's sending, what it's receiving. This is basically what it's sending to our URL that we just built here. It's basically sending 5 time series, each time series having 10 days, if you will, or 10 time steps. So that is the matrix that it's sending. So it's you can make predictions batch here, just a batch of 5 time series. It's getting a response back here. And I'm printing that too. Just knowing what the time is. So this is and I'm sure if I run this another time, it's going to give me less. So there's this overhead of first time running and loading those packages. Typically, it drops to about 5 milliseconds. So it's very fast to the communication essentially between 2 random nodes in the data center, as well as TensorFlow Serving taking the time to make the prediction. So communication plus prediction time, back and forth, everything under 5 milliseconds. So it's actually pretty good. And this is plotting the outputs as it receives. So we can just validate what is it that it's receiving. So I think we're good here. So on the client side, just a few notes. If you want to do more optimization, if you want to improve the performance further, if there's some problem you want to do more optimization, you can always use protobuf for data serialization. So we just sent a JSON clear text. You can compress that further if you need to, and GPRC for communication. This sample code is not, the delays are within the acceptable range for us for actually every application in recent memory. But if you need to go high performance for whatever, depending on what you're working on, there are options to optimize that and bring that 5 millisecond basically lower if you need to. The codes are on GitHub, so this is so the URL is there. You can just grab everything that I just showed you today. I'll probably share this few slides as well, but that is you can take a picture and have the URL right now while you're at it. If you have feedbacks, just contact me directly or send an email to research@patterns.science. Obviously, we are on LinkedIn, so if there are events we co-organize, co-sponsor, follow the page so that you get the announcements. We are planning several events/meetups in the next few months, so that's probably one place that you will get for sure an announcement at the event. So I have few actually minutes for questions. Yeah, go ahead. Actually, probably do you want to grab a mic?
So most of the code you showed, it seemed like it was kind of like nuts and bolts of pass and gather around the various components and parts of the program. But there is one thing at the very beginning is you defined an array called params. And I was wondering if you could elaborate on your choice of parameters, such as like the topology of the actual network. Like, I don't know what the model looks like.
So the model is actually, the graph you remember that I just showed. So this is basically, the ones that you see are chosen at the top are basically Guillaume's choices that I kept. So he's using some variables, and there's not much complexity. It's basically in any deep learning and machine learning model, these are the neighborhood of numbers you want to start with to train that. So there's no black art, frankly, to that. It's a known starting point in majority of them. But the rest of it is just somewhat randomly picking a parameter and just grid searching over it to see if it gives you more. But that's the best answer I can give you.
So my question is, do you think it would be possible to define the same type of sequence-to-sequence models using Keras on top of TensorFlow? And do you think, if that's the case, do you think that it would reduce the boilerplate code that you were showing? So
that is an excellent question. It depends on how comfortable you are with writing boilerplate code. So if you are a TensorFlow developer, much of this goes fast. Basically, I personally copy-paste from my earlier works. It really goes fast. So once you learn it, it looks maybe frightening to a newbie, but it's really fast for someone who knows. So when you have working with a lower level API, you have all these knobs that you can change, and it's in front of you. You can change quickly. So with Keras, it's higher layer. Some of it you can do, but I'm not sure how complicated it is if you now want to change something that Keras doesn't give you the right API, so that you have to work around it and call TensorFlow API itself directly because you want to change one part. Then it becomes it's like it defeats the purpose. So I would say, if you are new to the field, for somebody who is new to the field, pick up Keras. But once you are comfortable with the whole thing, I wouldn't see a difference. Personally, for me, it doesn't make a difference.
I was wondering, in the context of production, if you want to have an ongoing prediction, do you have any sort of pointers for general rules of thumb for how you go about not doing like a single batch prediction, but sort of an ongoing prediction process?
So this is basically the server is listening. You can throw at it as much as you want, as fast as you want. We haven't done a stress test on to see at which point it's going to fail. We haven't hit that part. It's not a big data streaming application here. We didn't develop that for the few applications we are using this, it's working just fine. But if you want to throw big data streaming, then for sure you have to do some sort of load balancing, over a cluster of TensorFlow Serving, or do, I don't know, maybe a cluster, a Kubernetes cluster even. So those parts are, I would say, out of scope. You need to, basically do this solution design based on what you really have. So I'll take one question, and then we can have chat in the breaks, because I want to leave some time for the rest of it. Just one more.
I wanted to ask you, did you use LSTM cells or GRU cells, and why, and which one would have been the best in this specific project?
So this was GRU. This was gated recurrent units, but the LSTM would give you the same performance. There's not much of a change of performance between one to the next. I don't have a deeper explanation for that. Okay, thanks very much, everyone.